Yeah.
Yeah, but you need a coffee.
Okay.
Yeah, and
Yoko?
I just went out to a sort of business dinner but I'm good now. I'm here. You've got my full attention. And has the meeting started? When are we starting?
Yes, no,
We're letting the participant to join the meeting now.
Okay.
Okay. Yoko is joining us, or is she?
Yeah.
I miss her a little bit.
She's not here now.
Mm-hmm.
I hope she can join.
Yoko didn't answer you, the organizers? No? She's not coming?
Usually she'll come.
Yeah.
I will message her, see whether she will join shortly or not.
Yesterday she asked for the link for this webinar, so I don't know. But I think she tried to join this webinar too.
Okay, we have about 70 attendees here. Maybe we can start the webinar now.
Okay.
Dear Professor Nobs and also Professor Basso, the time is yours.
Yeah, Armando, I think it's
okay. Can we start?
Yes, you may start.
Okay, good. Well, my dear friends, you know, I'm surprised, but in a good sense, because when we found this International Society of Minimal Invasive Technique in Neurosurgery, 2012 in Florence, in Italy, the idea was follow the steps of our dear friend Axel Pernesky, because the minimal invasive idea started with him with the philosophy of minimal invasive for surgical technique, the keyhole approach, and so and so. Then little by little, the idea of minimal invasive was moving to some other ideas of in neurosurgery. That's been minimal invasive approaches, but with maximal good results. That was the philosophical idea. This time, my good surprise with this webinar is that we are doing now a step forward or two different approaches to the philosophy of minimal invasive in neurosurgery. So it's my enormous pleasure to introduce, and I let Engelbert to show us the introduction for our extraordinary speakers. I'm very, very curious to learn about connectivity, rewiring, and all things that really for me is fantastic. I will learn certainly a lot from you. So it's my great pleasure to be here and share with you this webinar. So Engelbert, please.
Thank you for this introduction. And I tried to bring the talk here with the slides which Armando announced. Thank you for the organizers to do that so precisely and nice. These are the pictures of the first International Congress on ISMINS in Florence, 2012. You see our charming Yoko Kato is president of our society here, and other well-known neurosurgeons from Europe. And you see Charlie here over the side.
Engelbert,
this was one of the...
Engelbert, sorry to interrupt, but your screen is not being shared at the moment, so we can't see it.
Okay. That's... This makes me difficult. You do not see that at all?
No.
We don't see it.
No.
Oh. How can we...
You have to go back to share screen, and then you have to click on the picture of your screen.
The picture to
so stop
that?
sharing first. You go to stop sharing, and then you share again, and you have to pick the screen that you want to see. Click on it and then share.
Yeah, this, but there is not the. Maybe I try it from my screen to open that. Now you can see that?
Not yet.
No, not yet.
Again? You do not see that?
Not yet.
Not yet, Engelbert.
Oh. How to do that? Open. No, this is the screen, and there was. Oh, this is the tragedy.
So if you hit the share
I tried
screen
it before.
and then the one in the upper left is usually the right one. The one that when the pop-up comes up, go to the window in the upper left. And double click that, and yep, there you go.
There we go. There you go.
That's with sales. This is not
we can
mine.
see that. We can see it.
And this, you see now the.
Yes, we see it.
Yes. That's
see
fine.
the presentation.
Yes, bro.
Yes.
Okay. With
now we see all the slides are put.
You can see. Okay, I will. The picture of that's it. You see the pictures.
Perfect.
Okay.
Perfect.
Again, the president and numerous neurosurgeons, and this was one of the big business meeting in Geneva. So it all starts with the Congress of Axel Panetsky in Wiesbaden at 93. So that's almost 20 years, 30 years ago. And then to remember of that, which combines in many of our friends here in the ISMIN business, is the endoscope. This is the first ever built endoscope in 1806. And this was the dreams of Axel Panetsky, with a platform, with a exoscope, the endoscope combined in the brain, and the 3D endoscope. This is one of the pictures in the OR in Mainz at that time, and this was his vision of the OR he wants to construct and to follow up. Coming to the topic, these are the Klingler's dissections of long tracts, of the fiber tracts in the brain. And this is one of the specimens in our courses. We did that. And if you see the fibers, you believe on them. And so we did for so many years a combined fiber dissection course with the ability with the DTI detection with the MRI. And I think that's what we do that. And I think the presentations we will see in a few minutes is that what are big questions. Quo vadis neurosurgery, and like other big announcements for congresses and that, Mike Buzzo, the realm of the high technology, I think the main problem in our presentations, possibilities, practicalities, and realities. And this is the last slide. These are the technologies we use every day. And there are questions in that, with a gamma knife, including the molecular genome, the genome, and other questions. I think more questions than answers. And I think many of the answers will be coming to the next presentations given by Sigrid Michael. Thank you so far. That's it.
Yep. So I guess I'll get going.
It's Amanda. Do you
Yes,
like to introduce Sigrid Michael or?
No, go on.
No. Okay. Who does not know Sigrid Michael? He is a neurosurgeon, and he had his education at the Columbia University from 2002 to 2005. He had his residency at the UCSF in San Francisco, and then he became the chief of the Health Science Center in Oklahoma University. And since 2 years, almost 4 years in Prince Wales Hospital in Sydney. And beside the job as a neurosurgeon, he is CMO of the Omniscience Neurotechnology company. So we are looking forward to see your presentation, Michael.
Well, thanks for having me, guys, and thank everyone for giving me the opportunity to speak. What I'm going to talk about is something that when I first got into the field of connectivity and I really began to grasp what was possible in the field, it became very obvious to me that this is something that we as neurosurgeons were going to need to adopt to, because it's a non-trivial contribution to our field. And I've given this talk now probably close to about 300 times on almost every continent. And over time, I've really started to refine what it was. Originally, it was a talk about anatomy. But reality, what we're talking about is going back to the core of why I got interested in this topic in the first place, which was how do we reduce the cognitive footprint of brain surgery? So what do I mean by that? Well, we all know that our goal when we tackle an interaxial supratentorial brain tumor like a glioma is to make the scan on the left look like the scan on the far right with as few problems as possible. Now, we're pretty good at understanding the anatomy of the sensory motor system. At least we know not to cut the corticospinal tract. We have a reasonable understanding of the basics of language, particularly the speech pathing. And with speech mapping, we can often keep the morbidity of that to very reasonable. But one of the challenges as we begin to get to the point where the really serious problems are things that don't happen very often in these patients we can avoid them in. One of the things we're left with, which is, what about the patients who we think are doing fine, but they're really doing neurosurgical fine, meaning that they move everything. But when you talk to them, they're not really fine. They have cognitive problems, their personalities have changed. And we know that the reason that's happening is that we're cutting something that's important. We know that gliomas often have function running through the parts of the tumor, and we don't really have a good understanding of how the brain does higher cognitive functions in the first place. So we don't have a real good way to avoid this. What this talk is about is how can we use machine learning to really tackle the extreme complexity of what we're asked to treat, and to really begin to eliminate this problem from our practice. So it's also important to know when we talk about the concept of onco-functional balance, which is a term that Hugh Defoe introduced, we have to really think about both onco and functional, because it isn't just enough to say, hey, let's not cause a neurological deficit. Sometimes it's unavoidable. Sometimes it's already happened. And furthermore, if you take the patient on the right and you under-resect their tumor and you think you're doing them a favor, well, you can't. If you don't control something this bad, it doesn't really matter what neurological functions you're saving. They're going to be gone eventually. So the first step, we have to think about the oncological considerations, and we have to get these kind of problems under control. But at the same time, it's hard to say that this patient on the right is well served by being super aggressive to get one more cc of tumor out and leaving them densely aphasic. So we all kind of know these things, which is that we're always making a trade-off. And because we can't cure this with surgery by itself, we're always basically balancing oncological and functional considerations. This is true no matter what we're treating, but with gliomas, this is a really stark decision. And one of the things that as I began to start thinking about this, and I've been thinking about this since I was a junior resident at UCSF and talking to patients' families at 2 o'clock in the morning, who they called the operator and said, "I'm worried about my son," but reality, they didn't have meningitis and they're moving all fours. So as a neurosurgery resident, you think, why are you calling me about this at 2 in the morning? But the reality is it's because they're concerned about it. And part of this is that we don't know how to save cognition, and the patients notice this even if we don't consider this an emergency. And so the time-tested rule is don't operate in the eloquent areas, or if you do, be very careful. And the point of it is, this is a really simplistic view of the brain. So it's hard to believe that the human neocortex, with a huge amount of frontal lobe and all the things that it has, just evolves all these structures to suck CSF or insulate the motor cortex. So we all know that this is a foolish way to think about the brain, but this is kind of how we all have thought about it for a very long time. And the reason for this is that we kind of understand the anatomy of the eloquent areas. We don't understand the quote unquote association cortex, which is really a terrible term. And so we don't really spend a lot of time thinking about how to operate in it because, well, we don't have any chance of saving anything there. So we just assume that it can't be that important. Now, someone wrote a paper a few years ago in the JNS that said everything is eloquent. When I thought about this, that's the silliest thing I ever heard in my life, because we think of eloquent as it causes a deficit when we cut into it. And we know that we can cut into parts of the brain. So that's really an oversimplistic term on this. What we're really talking about is that everything in the brain is in the playing field, and we get away with some things because there's redundancy in the system. And so people have also talked about, what if we did cortical stimulation? And brain mapping worked really well for language, and it worked really well for motor. Why can't it work well for cognitive function? And I'll give you some reasons why that's probably not true. There may be some applications that people have been able to get some reasonable success at. I have personally not been able to do this in any way that is convincing to me. And part of it is because I don't think these areas are in one place in the brain. I don't think intraoperative tests very often give us clear answers that I would say leave tumor behind to save this. And do we really understand what we're trying to preserve? And if we don't understand what the anatomy of what we're trying to not cut, because the cerebrum, we do not see the anatomy most of the time. The deep white matter doesn't have a visible anatomy. If we don't know what we're trying to do, we don't have a real good chance of not doing it. So what I'm going to try to convince you is that, and I think many people else, the other talks in this discussion are trying to convince you, is that the brain is the most complicated thing in the universe that we're aware of. And in order to really tackle this, we need to stop getting past thinking in terms of this is something that human brains can solve. If it was possible to resolve the human brain by thinking about it, we wouldn't have a sophisticated enough brain to think about how the brain works. So we need data, and we need machine learning and some of the tools that are able to handle very complex data sets. And as we learn to and reduce our uncertainty of how the human brain does these functions in the patient we're operating on, we adjust our thinking to balance oncological and functional considerations. So what I propose is a 4-step plan on how we as a specialty can start to reduce the cognitive footprint. So the simplest one is this. The real organizing principle of the human brain, and I'll also show you, are large-scale brain networks. The data on this is crystal clear. There's tens of thousands of papers talking about large-scale brain networks, and we should try not to destroy them unnecessarily. Sometimes it's not possible to do that, but whenever possible, we should not destroy the middle brain networks. And I'll try to convince you of that in this talk. The second is that just saving the brain networks may not necessarily reduce all of these problems. And there may be thinking about the brain as a global system may also be helpful. I'll briefly touch on this at the end of my talk. Stefan is going to talk about how do we move our thinking towards individual circuits, and how do we really leverage artificial intelligence or machine learning to really dig into the complexity of the brain. And finally, given that we know the connectome is plastic, can we change it? And the answer, we think, in many cases is yes. And this is what Charlie's going to touch on in the final talk. So I'll kind of dive into the first two talks and introduce what the concept of connectomics means. So omics comes from the term genomics, which is big data for genes. So connectomics is big data for connections. And mostly this is MRI based, because the other ways you can study connectomics involve things like electron microscopy and things that we're not really doing on patients who are living anymore. And as a result, really connectomics is about leveraging MRI data, particularly functional MRI and DTI, to really start to learn about how the brain is wired up on a global scale. Now, fMRI and DTI are not new. They've been around for 30 years. There's at least 550,000 papers, and pretty much nobody reasonable debates that there's actually knowledge in the data sets and that it's valid and relates to brain function. So while there's some limitations and people make a big deal about them, the bottom line is it's pretty clear that these are telling us something useful. So then the question is, why isn't this something that we do on every single patient we see? You know, again, I would ask, you know, we get all these flares and ADCs with our images, and sometimes that's useful, but most of the time this is not that useful. And it's hard to argue that a well-done functional MRI that shows high-level connectivity features is wouldn't be more useful. And given that most scanners can acquire this, why don't we do it? Well, it's simple. It's a real pain to get this done. We all know this. Oftentimes, task-based fMRI is even more painful, and it's just not able to be done on a regular basis in a clinical scanner. When you get it, you have to have people know what they're doing, and those people don't work weekends, and they're kind of busy, and this becomes such a big deal that we don't use it often, and as a result, we don't know what to do with the information, because if we don't do it all the time, we're not good at it. That's pretty basic clinical experience of almost anything we talk about. And what has happened, and one of the reasons why we get these very pretty pictures that are good for grants, good in papers, wallpaper and posters on the wall and things like this. But again, this hasn't really cracked the nut, isn't because this isn't giving us a great map of the brain. There's amazing stuff people have done with DTI. But most of it, when you actually see what people show off, it's the corticospinal tract. And why do they do that? Because we know what the corticospinal tract is basically doing. And so as a result, that's one of the millions of fiber bundles in the brain that we actually have spent an inordinate amount of time finding. And the reason is because we don't know what the rest of it's doing, and so we don't care about it that much, even though it could be what makes that person who they are. And so in order to handle this, we have to recognize that the brain is a very high dimensional equation. There's lots and lots of things going on in here. And this is not something we're going to eyeball and figure out. We need help. This is an fMRI, and this is what comes off the scanner. Now, this is not useful. So if anyone looks at this and thinks that this image provides clinical utility compared to almost anything we do, T2, flare, T1, contrast, whatever, it's not realistic. But what computers can do is they can actually go to every voxel, and they could find the bold signal. This is the activation signal of the cortex. So there's a lot of information in there. But when we think about the fact that this bold signal is happening at every single voxel in the MRI, it's really important to know that ultimately this is an extremely high dimensional rich data set. There's things in the set, that little area is changing who it's talking to at almost every time point in the scan. And so this is, again, not something that human beings are good at looking at. And more importantly, it's extremely complex data. And so if we basically just give you this thing, it's not useful, right? And so in order to make it useful, really what's cracked the nut open is artificial intelligence / machine learning. It's being able to go in there and cut this down to a size of data. And when you get into machine learning, and Stefan will talk about this a little bit, when you deal with lots and lots of variables, one of the most important steps you do is dimensionality reduction. And there's lots of ways to do it, but get the machine learning down to a smaller number of dimensions than a billion or a million or whatever you're dealing with. And the best way that we know of is parcellation. So what does that mean? Parcellation is to take the cortex and divide it into areas based on function or structure or cytoarchitecture or whatever you want to base it on, some criteria. And everyone here knows at least one of those. It's called Brodmann's area. So people have been parcellating the cortex at least since 1908 based on some kind of different criteria. This one you're looking at here is actually my brain passed through the Human Connectome Project scheme. And this was made in published in Nature in 2016. And what they, instead of 47 areas, they concluded there's about 180 unique cortical areas. And if you look at other efforts to do this, there's at least 7 or 8 different parcellation schemes wandering around that have been made recently. And they're all kind of in that range. So there's somewhere between 140 and about 250, depending on what criteria you use. So we know that the brain is a little more complicated than what Brodmann was talking about. But more importantly, one of the things that struck me when I saw this paper, and actually someone gave it to me the week it came out, and I was working on DTI at the time, and I immediately went to work on this almost the moment I saw it, because there were some things that were really striking. One of which is that if you look here in the insula, there's the undersurface of Broca's area on the opercular cortex is a totally different area than the outer surface. It does something different. It's not part of the same network. They talk to each other because they're neighbors, but other than that, they're not really similar areas. And there's also areas that sit inside sulcuses. There's gyri that, for example, the supratemporal gyrus isn't one area, it's actually 10. And so when we think about this, the brain doesn't care what we call gyri and sulci. That's why they're not consistent. It has nothing to do with function. The brain puts function wherever it wants to put function. What's also interesting is that they found that these are relatively consistent. So while this may differ a little bit between people, the boundaries are not that variable. They differ by a few percent. And one of the things we looked at this when we saw this, and why we spent a lot of time with this, is that it allowed us to have an alphabet that we could describe brain function. So if we're talking about 8C, which you can see in the upper left is dead center, we're all talking about the same area, and that area is valid. So we started writing anatomy, and we wrote, we started just doing a ton of work. And eventually this got up to about 17 or 18 papers. And we talked to Nelson Oishiku and said, can we put this in one place? And he let us do that. And so, as you can see, this was a very detailed, and anyone who's read this, kudos. It's about 500 pages long, where we mapped out everything conceivably possible, what was going through what white matter bundle, et cetera. Now, one of the things about it is we had so much information that ultimately, do I expect that people are going to basically memorize this like a Roten manual? Well, I kind of know those areas like that, but it's not realistic that that's going to really be adopted in neurosurgery. And in order for us to actually use this realistically, we have to be able to atlas the brain. And what that means is I need to go in the brain of the patient I'm seeing and assign every part of the cortex to one of these parcellations. Say, okay, who are you? And the typical way this has been done is you take the atlas and you warp it till it fits the brain that you're going on. That does okay, except you can see here at about 8 o'clock on this brain, right where that arrow is, it missed its sulcus. And we know that that's going to happen. And there's some tricks around that, but ultimately none of them really were very satisfying for the kind of patients I saw, which is this. We know that the atlas is going to be wrong here because the brain is distorted, things are shifted, and that just doesn't even count in the possibility that there's been plasticity changes that change how the brain is wired. So when I met with Stefan and a few other people, I brought this idea to them, and we came up with a technique called reparcelation. So what that basically does is a machine learning technique where instead of assigning the region based on where it was located, we based it on who it was connected to. So what that means is we taught the machine what a voxel of Broca's area looks like. And so what it learns is that if you're connected to the SMA or to Wernicke's area, you belong in Broca's area. So it goes around and looks at every voxel in the area and says, are you Broca's area, yes or no? So this guy is a no because he's not going to the correct area. And there's another one back here that is going to get assigned because he's connected to Wernicke's area. So you get into the parcellation. And that allows you to adjust the boundary to account for this and give a personalized atlas. So there's nothing in the sulcus or a hole in the cavity. But more importantly, if it tries to move the parcellation into the middle of a tumor or the brain is reorganized, well, the tracks are going to be moved around too. So it will actually adjust that boundary. And so what this means is that we can actually assign an atlas to anybody and handle neuroplasticity differently. And so, for example, this is the worst brain I had in my collection. Somebody did a DTI in this that we did not operate. You can see that there's been a frontal lobectomy. The insula on the right side of this image, left side of the patient, is shifted anteriorly. There's a huge recurrent glioblastoma. And despite that, it's able to actually see the basal ganglia correctly. It's actually able to also tell us what's missing and how things are reorganized around a tumor. So that's a level of insight that we've never really had before. And what this allows us to do is to go into these really complicated cases and have a reasonable idea what the anatomy is. And so not that we operated on this or this was even a surgical case, but the reality is we could at least have some prayer to guess where the basal ganglia is. So because of that, we can start to think about how do we preserve large-scale brain networks. So I'm going to give you a taste of what that means. So if you look at this tumor, we've known it's been bad for a long time. We know that many of these patients have cognitive problems. The strange part is, why is it not vision? Why is it cognitive and memory and not vision? And we also know that if you go in there blindly, it's a fair chance you're going to make somebody's cognition pretty bad, and maybe even other things. Even if you're careful, you don't hit the thalamus or some major tract. And so now what we can do is we can actually see the anatomy of the brain networks, the sensory motor network, the language network, and a network that many people probably haven't heard of if you're not paying attention, which is the default mode network. And the reason you haven't heard of this is that this was discovered in about 2001. And since then, it's blossomed in neuroscience, psychiatry, and many other fields. It's over 10,000 papers about this. It's basically one of the dominant cognitive networks of the human brain. There's no doubt about this at this point. And it never really made it over to neurosurgery because of silos, really. Ultimately, people weren't going to the right meetings where information was being shared between the neuroscience community who knew about this and neurosurgeons who were actually needing to know this information. But we now know that a butterfly glioma is almost 270s this tumor, because that's just how the corpus callosum links to the cingulate where this tumor, the DMN, is based. And so while we may or may not be able to operate on this, this is an opinion that different people will hold. The bottom line is we can actually take even a really complicated, nasty case and break it down into what actually we're cutting next to and how do we preserve networks, which would improve our chances of actually saving them. And of course, you can imagine with simpler situations that this is much more salient. So I've used the word network, and what do I mean by that? Well, what we know now is that the concept that there's a language area or a visual area, and there's some other areas for memory and things like this, the frontal lobe, for example, is just not consistent with the data. So we know better what explains this, that there are areas in different parts of the brain that are usually wired together that fire commonly at the same time. Not all the time, but they're often firing simultaneously. That's why we call them a network. And we know that they do that in most of the time because they have common functions in common. And what ultimately, this is much more closer to the foundational basis of how cognition and other functions in the cerebrum happen. And when I first started getting into this, of course, I'm a type of person who likes to be thorough and check all the boxes. And I want to know how many networks there were. And turns out there's all sorts of different ways to name networks. And part of the confusion is not just nomenclature, but so many of these networks subdivide if you use different statistical thresholds. So there are basically 7 core networks. But if you're more rigorous, some of these networks break into half, and they're, so I'll show you, for example, in the default mode network, which is a large portion of the brain, there's at least 8 different subcomponents, one of which is the language system. So the language system fires closer to the DMN than any of the other 7 networks, but it's closer to the language system than it is to the DMN. And so this is where it becomes complex. But the bottom line is there's 7 main networks. And if you take the brain and assign everything to its closest network, this is what it looks like. Now, you probably know that one, and you probably know that one. And the limbic system seems mostly familiar. Note that the temporal pole and the orbitofrontal cortex is included in this. But also the central executive network in orange, this is new to most neurosurgeons. The red DMN, we can see it's large portions of the brain synchronized with at least the core of the DMN. The salience network, this wasn't even known about by anybody until about 2008. And the dorsal attention network in green. Yeah, so these are the 7 main networks. And what we decided to do when I first did this is we wanted to say, let's figure out in this scheme, who are the parts of the networks? Because if we can map it with an atlas and we know that you're part of a network, we can make a model of a network. So what we did is we went out into everything in the fMRI literature. And if someone had cited a point and said, this is the DMN, we took that point and we did a statistical analysis called ALE, which is what you're seeing there. And that's telling you, this is the summary of the world's literature what's activated when you do a language task in this case. And so we match those to parcellations. And then we have a map of the network. Now notice this is the language network, and this is a lot more complicated than broken warning. Yeah, I'll talk about that in a bit. There's two things that I think we need to have a serious update as a specialty, because our understanding is not only woefully out of date, it's now that we have an understanding of what the consequences of destroying these areas are, it's becoming increasingly difficult to justify not thinking about this when we do surgery. And one of the concepts that's come out of modern neuroscience in the last 20 years is the concept of the control networks. So what that means is that realistically we have two basic brain states. One is the thinking to yourself internal state, which is dominated by DMN functions. And the other is the central executive network, which is an external goal-directed state. So you got to snap out of your internal mental state of daydreaming and get to action is the best way to think about it. And the third network that mediates that's the salience network. It's the gear shift that settles the arguments between these two. Notably, these are not supposed to fire at the same time. In fact, if they fire at the same time, that's actually one of the fundamental bases of psychiatric mental illnesses is problems in the system. So it shouldn't surprise us that when you operate on people and destroy some of this stuff, we get some people who have depression or other mental problems afterwards. Now, we've looked at the cingulum for a long time. In medical school, I was taught that this was part of the Papez circuit, which is memory. And this is actually a very small portion of what the cingulum actually does. Now, what we didn't pay attention to is all these fibers that are leaving. They just kind of look like extra noise. We just saw the beautiful track bundle. But the reality is that those things leaving are the most important part, because if you look at this, this is our map of the cingulum. And you can see that this could be almost a talk by itself. But if you look there, those are those fibers, and there's a lot of things connected there. This is the posterior cingulate gyrus, and it's the most functionally connected part of the human brain. There's nothing that drives and controls the activity of more areas than that we know of, other than the thalamus and the brainstem. And if you look at it, it's the epicenter of the default mode network. Now, again, the default mode network has lots of sub-networks that are kind of its satellite states, but the core of it is an anterior cingulate, posterior cingulate linked by the cingulum, and a lateral parietal area, so three parts. The salience network is that gear shift I talked about, and it's the middle cingulate and anterior insula linked by the frontal aslant tract. You can see there on the left. And the central executive network is the frontal pole connected to the supramarginal gyrus with that area 8C that I mentioned earlier intervening. It's a very important part of the brain as well. Now, if you look at the functions that have been linked to this, it's extensive. This is a very, very short list. Most mental illnesses have problems with the default mode network, but we think about it in terms of internal thoughts, imagination, episodic memory, et cetera, et cetera. Memory, for example, is heavily influenced by the DMN. The salience network is part of lots of aspects of emotional regulation. In fact, it's the network that's most abnormal in depression, but also it's how pain is mitigated. So many people who have chronic pain have been shown to have abnormality of how the salience network works. So this kind of makes sense why a lot of chronic pain patients also have depression or other problems. It's the same network. The central executive network is what it says it is, things like working memory and executive function. And the dorsal attention network that I briefly talked about is better thought of as an IQ network, because anything a task that you would use in an IQ test requires directed attention, and that's the DAN. Where this becomes powerful is when we look at how these networks talk to each other. So if you can see, you have the default mode network talking to the salience network, and the salience network is part of the SMA. In fact, the SMA is just the DMN and salience networks meeting around the motor system. That's actually what the SMA is. Now, why do I call it free will? Well, we know that the medial frontal lobe, if you injure it, you get an akinetic mutism. But we found that if you do that doing surgery, you leave people akinetic mutes, and if you save it, you don't do that so much. And this group from Harvard independently found that the only ways you become an akinetic mute is an injury to the thalamus and upper brainstem, or the injury to the system. So we now have a new eloquent part of the brain, which is the initiation axis. And there's even people who started, since I introduced this topic, talking about the initiation axis syndrome, which is distinct from SMA. You don't get a hemiplegia, you just don't do very much. Another model that Connectomics has upgraded is this one. It's hard for us to really justify that we're still using this in 2021, given how long the broken Wernicke have been dead. And it's not that it's wrong, it's that it's incomplete. We know that it's incomplete from work from many people who found that there are other cognitive syndromes, particularly from the left temporal pole, that don't fit into the model very well, particularly for dementia or doing temporal lobectomies for epilepsy. But even if you talk about how speech is processed, it's more complicated than the Broca-Wernicke model. So this is our model. And you can see that I put an arrow to that area 55B. Now, that was not discovered until 2016. But since then, Eddie Cheng at UCSF has published a cell paper, and I worked with him to publish a case report after he told me about the cell paper that was about to come out. And we found that this is probably a motor cortex of the larynx. More recently, a group in Spain validated this in a large series. So this is not connected to Broca's area at all. It has its own independent connections to the temporal lobe and is a small area that sits in a sulcus that we never thought about because we didn't split the sulcus to look for it. And this is a patient that I had. There's a case report in neurosurgery posted sometime last year. And we did a relatively modest resection of this tumor. And for 8 years, I had no idea why this guy couldn't talk, even though he could write an email showing that he has almost perfect language function. But he doesn't have speech function. And when we had a professional linguist study him for over 8 hours, including putting a scope down his throat, the only problem is the larynx. And so this is a real thing. And this was not something that most people had in their thought of where language is located in the human brain. Again, when we start talking about language, and without going into too much detail in the interest of time, this shows a paper that's about to come out in operative neurosurgery where we've looked at how the temporal pole talks to the language system. And what we've shown is that it has a unique fiber bundle of white matter fibers that parallel the middle temporal gyrus that make it part of the default mode network. And that this is not a speech pathway, it's a language. It's a language pathway in that it's the cognitive aspects of speech. So when we look at all the things that you add to it, this is really what the model is closer to. And again, this can take additional revision, but we should need to start thinking about these things, because when we have language problems that we don't understand, we can't just go look at broken Wernicke because it's an incomplete model. Finally, I'm going to show one thing that I think is really cool. So the 7 networks pointed out again, and if you look at this, this seems really random, but truth is it's actually not random at all. So if you look at the midline right here, you notice that that's not an accident. That looks like patterning and that we see in embryology. And furthermore, when we look at the default mode network, it makes this sort of S shape. But we notice that the CN does that same thing. Posterior cingulate, anterior cingulate, gone to the frontal lobe, over to the SMG, and then down to the temporal lobe. And the salience network does the same thing, and the dorsal attention network does part of that trip. In fact, this has been repeatedly shown all the way down to at least marmosets that this is how the brain evolved throughout time. And it's also not an accident when we look at the cerebellum. So if you look at this in the coronal section, notice that the red is DMN, and that's the vermis. So we've always wondered how cerebellar mutism happens, but when you think about the default mode network is manifested in the vermis, and the default mode network includes components that are in the language system, it should make a lot more sense how this might be going on. But if you look at it in parasagittal section, and that's what you're looking at here, you see this amazing feature, which is that majority of the cerebellum and the cerebellar hemisphere is actually the default mode, salience, CN, and DAN, and that they follow this pattern. If you start at 1 o'clock and work counterclockwise, sensory motor, salience, CN, DMN, and then on the inferior side, it reverses. And this is also replicated in the basal ganglia. So there's something about the organization of the brain that is really based around these networks. So how do we use this? And I finished writing a book about this. It was published a few years ago. And this predates our having software on this. And what we were working towards is, instead of talking about, entry points in eloquence versus non-eloquence, we think about, because again, sometimes this fails us. We have a lot more cognitive morbidity than we admit if you spend time talking to these patients that are doing neuropsych tests. And part of what we should think about is that we're cutting next to brain networks, and we should plan the operation to say, how do I make sure that I don't cut through them? Because the brain didn't evolve as CSF sponges. It's doing something, and what we should try to do is at least not cut through the middle of networks. That's something achievable. And what we're trying to do is think about, how do we make a cut, but that's safe. And again, one of the biggest differences between glioma surgery and skull-based surgery is, in skull-based surgery, it's very technically complex. There's lots of anatomy, but it's all visible. So you can sit there, and once you understand it, you see most of the structures, and you can understand where they're probably going to be based on the pathology. Whereas we never see that. No matter how good you are at gliomas, you never see it. It might be in the tumor, and you're just looking at this white blob. And so what we need to do is to utilize adjuvants like tractography to put anatomy back into the picture, so we have a basic idea of what we're there to do. And so these are some pictures from the book where we showed safe disconnections, how to cut next to networks. Now, you wouldn't always do a frontal lobectomy here, but what you would try to do is think about whatever you're doing to preserve things like the salience network, DMN, et cetera. And so turns out that can be automated, because if we can make pictures of networks, we know who the parcellations that follow networks, we have a good idea what they're doing, and we can put this into a workflow. We could just set up a workflow where you could say, I want to be in this part of the brain, and it spits those networks out so that you have it on your image guidance. So we got this product through the FDA. It's called QuickTome. It's going to be launching worldwide later throughout this year, and it basically automates this entire process. So that essentially, that's the map that you get on your image guidance, which is the modern language map that I just showed you. Now, when we start thinking about how to use these things, what we're using them is to set goalposts. And so when you look at this tumor here and you see that this is very large and complex, again, you could think about starting at the frontal pole and working backwards. But the truth of it is, at some point, you're cutting next to the network. And so why not make that the key part of the operation that you do as early as possible? Because once you've done that, everything in front of that is basically a meningioma. And so instead of doing this in a disorganized fashion, removing it circumferentially, you basically can now see the default mode network, the CEN, and the sensory motor network, and you have the cuts that are defined. Now, maybe you can't save the DMN. There's some situations where there might be cancer into it. And we've had cases where we've decided to sacrifice the DMN and then utilize things like TMS, like Charlie talked about, but to augment and help people recover from that. That's an oncological choice. But what you're not doing is, you're not doing that on accident. You're not doing this because you don't have an idea where it's located. And that's really a big difference, is that we can still make difficult decisions, but we can do this based on data. So one more thing about the whole brain ramifications. And so it's not good. It's good to not cut through the middle networks. But what about things like mathematics? Well, we've mapped that, and it's a multi-network function. And so this may have connections that are almost too complicated for me to make a map of that's useful. And so when we start looking at network theory and graph theory, it provides a way for us to mathematically study this. And so what you can do is, you take the brain, you do your tractography, you parcellate it, and then you calculate how many fibers go between every point and every other point. And now you have a big math equation. And that looks cool, but there's some unique experiments you can do on this. And one of them you can say is, who are the hubs of this network? How does information flow in this network? And if you look at the thing on the right, this is how Google initially tackled this problem when they made their search engine. But it's actually a useful tool for looking at the brain and saying, who's the most connected area, or the hub? We know that hubs use energy differently, and they have different gene expression. So they're just fundamentally different parts of the brain. We also know that they're more susceptible to Alzheimer's. So we looked at it and said, okay, that's cool, but who are the hubs of the brain? And these are the top 10 based on ranking them. And if you were doing an AVM and you were trying to assign a Spencer Martin grade, Those red arrows get you the eloquence point, meaning everyone acknowledges they're the primary motor cortex, the visual system, etc. Undisputed, eloquent parts of the brain. So 6 of the top 10. And those guys should be on the list too. But I even gave this lecture to Spetzler and mentioned this, and he said, well, we didn't know about that back then. So the bottom line is they're important. And so finally, how often do we have hubs in the brain where most people don't, right? So we know that don't cut into the brainstem. The brainstem's the top hub here. And this diagram is a little bit complex, but we looked at this in 400 people. This is published in Journal of Neurology late last year. And what we were looking at was how often does it happen? We don't know if it's bad to cut into unexpected hubs, but it seems that the hubs are eloquent that we should consider them. And it turns out it's about 7% of the time. So for example, this area A10P here is in the frontal pole. And in most people, it's not an important part of the brain. But this one person with this red square, it's one of the biggest hubs in their brain. So it's up there with like the basal ganglia. And so we've always wondered why these patients that we do minor surgeries on sometimes do a lot worse than we expected. And the question is, are we missing some of these bigger picture whole brain features that only something like network theory can pull out? This is something that needs to be further explanation, but it's actually possible to show this and study it. And again, we know these patients, everyone here has had them where you don't think that you did that much and turns out you did a lot more than you thought. So I'll turn it over to Stefan to talk about how do we use machine learning to find signal and noise to get down to really to the level of individual parcellations in one patient and say what's important and what causes the symptoms they're having. Thanks, everyone.
Thank you, Michael. It was a fantastic lecture. It's worth to hear you longer than 20 minutes as thought before. Armando?
Yes, really fantastic lectures for everybody. The importance of connectomics and the importance of cartography, because this is the simple instrument that we have in our daily practice. Improve the connection, and the importance is not the anatomy, but who is connected someplace with the other. This is very important to transmit to a general neurosurgeon today.
And I think that, yeah, it's one of those things where a couple of years ago, no one knew this existed. 5 years ago, almost no one in neurosurgery knew about it, and now it's hard to ignore it. It's important parts of the brain that we didn't know were there.
Oh, fantastic! Congratulations. Oh, we should continue, Angel.
Yeah. It's a pleasure to welcome Stefan Toya. He comes from Brussels. He had his training there and in Cambridge, and he switched between Great Britain and Brussels many times. He is neuroscience in education, and he's also a neuropsychologist. And I think his main work now is the big data scientists, and these led him to come to Australia to be chief of the Omniscient Technology Research Group. It's yours, Stefan.
Thanks very much for the intro. I'll just share screen here. And hopefully this is coming through.
Yeah.
Can you see this well?
Yeah, wonderful.
Yeah, okay, great. So, well, thanks for the intro, and it is a pleasure and an honor to be able to speak to you this evening or morning or afternoon, wherever you are. And so, yes, as mentioned, I've spent about the last 15 years working in machine learning and AI. And so what I wanted to do in this talk is essentially to show you a view which will help to understand what type of a revolution machine learning and AI can bring to medicine, and specifically in the context of the brain. And so for this, I'm going to talk about three things. So I will start with a walk through the machine learning or AI landscape. And then we'll move on to explain how we can take the brain as a machine learning problem. And finally, we'll provide you some perspective of what it takes to build a software that is used for clinicians that takes into account the two previous topics. So first things first, often you hear the terms AI and machine learning, and they're often used interchangeably. As it turns out, the general field of artificial intelligence is what is called AI. And as a subfield of AI, we have machine learning. And the purpose of machine learning is to essentially learn representation of data with algorithms that weren't designed to do so. And within this, there is a subfield called deep learning, which I'll briefly hint further in presentation. And so AI is a very complex subject to grasp. And so people have thought of all sorts of ways to understand AI. And one of the things that was designed actually to judge whether a piece of software was artificial intelligence or not was a test designed by Alan Turing in 1950, so-called the imitation game or the Turing Test. And so Turing's definition was that if a computer is able to fool a person based on their prediction, when you put a computer and human side by side, and obviously the person doesn't see either of the two, then the computer qualifies to be called artificial intelligence. Obviously, things are a lot more complex, and I think what is important to see nowadays is that most of what we call AI is actually, in fact, machine learning. So what is machine learning? So very, very simply, we have this chart there where we put on a plot heights by weight. And so the most simple version of a machine learning model is simply drawing this regression line right there. And this line is indeed a model of how the weight and the height are related. And if I were to make a prediction of a specific height given a weight or the other way around, my best bet would be to place a point on this line, and I would be more or less right. So this is at the heart, this is a very simple of machine learning model. Other types of machine learning models that you might have heard of are called classifiers. Classifiers are telling things apart, let's say whether you're in one category or another. For instance, here, female versus male. And the simple classifier is just drawing this line here. And by predicting a point on one side of the line to another, we basically are able to get to a prediction of a class. So very simple. Obviously, things get a lot more complex. And so, for instance, you can look at height and weight, but you can also add in weight size and many more dimensions. And you end up using systems or algorithm to draw planes or decision boundaries so that you can tell apart observations or you can predict where observations are in space. So very simple explanation of what machine learning is. And so getting into the field of deep learning, what a deep learning, and that may talk slightly more to this audience, is an artificial neural network where we have a set of units, input units that are receiving data, and then output units that are making prediction, and a learning algorithm which will tell how the hidden layer in between should be tweaked in terms of how they connect and their weight, so that the prediction coming out of the output layer is closer and closer to what we're trying to predict. Such systems are extremely powerful because they deal with non-linearity, so predictions that suddenly jumped or are a function of another. They deal really well as well with high dimensional problems, such as what we see in brain data. And they're able to summarize that large data really well as create new features. So intermediate representations based on input data. So where is machine learning really good? What does it excel at? So here's a really interesting study I came across recently in the journal Science, which explains that some machine learning researchers here have been able to predict to a certain degree of accuracy mutations of the SARS-CoV-2 virus that is currently going around our planet. And they have done this by using techniques related to natural language processing, and have observed the mutation in the genomes that were grammatically correct versus non-grammatical genome that we can actually see on the right-hand side. This is a representation of the genetic material inside of the virus. So really, really interesting study in terms of accounting for all the complexity of the mutations that we can find and predicting the one that is more likely, and obviously great impact for potentially designing future vaccines. Here's another absolutely remarkable turning points in the field of machine learning was when Lee Sedol, which is a player of Go, was beaten by a computer. The Go game is an extremely complex game in the sense that the number of possible answers are far too many, so that even a modern computer can't compute the answer in time, and therefore we can't really establish rules for finding what the right answer is. Here, this machine learning or AI system was able to do so. And the beauty of it is that in order to be able to be doing this, the computer system had to review 2.5 million games. And if you think about a game taking about an hour, this would have taken a human being 300 years to go through. So immense amount of information, and the system was able to go through it and make sense of it. But there are still some failings. So machine learning is not perfect, is a kind of joke example really, but this is a translation of Estonian where the pronoun ta refers both to male and female, and you can see how the system is interpreting one or the other based on previous data that was fed into it. So machine learning, in summary, if we walk through that landscape, really is extremely effective at two things: reducing large amount of information, so finding signal and noise, and reducing complexity of information, so presenting what is really important. When we look at the medical field, there is quite a few very interesting examples, but some of those examples could be considered that time might be spent very well elsewhere. And so some may include, if you're familiar with, for instance, Kaggle, which is a great place for machine learning specialists, where they get to work together and produce the finest algorithm. Well, what we find is that a lot of the work is actually targeted at solving the obvious. Finding a tumor on an MRI scan, depending on the nature of the tumor, obviously, is something that is quite easy to do. There are other tasks that are far more complicated, and this is probably a better place to spend your time. Other things, obviously, are related to data, and it's inherently a problem in the field. So here's an example, for instance, from genome-wide association study, and it was found that in 2016, 81% of that data was actually data from white male Europeans. So when you're building algorithms that are meant to learn and produce prediction based on what they've learned from the data, well, if you're providing biased data, you will end up with biased algorithm, which obviously in the field of medicine is a very complex and non-trivial problem. Other thing to think about, particularly in the medical field, is what we consider to be an outlier or what we consider to be a new trend. And this is a very interesting data set. This is the average number of flights that are found around the world across several years, so spanning from 2016 to 2020. This is, in machine learning, the most studied time series data set. And what you find is that there are great algorithms that are able to predict very accurately which is the next point in the line for all the years ranging from 2016 to 2019, but somewhere in 2020, there is a sudden decline in the traffic, and obviously no algorithm was able to predict this. Even further, no algorithm nowadays would be able to predict the next point on this dark blue line, given that this is a unique situation and we haven't got enough data to learn from it. So very important issue when it comes to using machine learning in the field of medicine, which is outliers versus new trends. Other issue to consider is practicality. This is an absolutely exciting work that was recently disclosed by Google, actually in January this year, January last year. And they released a map of every single neurons and every single synapse in the brain of a Drosophila. It's actually even available online, so you can connect to the website and you can click and walk through. It is absolutely stunning. But is it practical? If you think about where we are and the computation power we have available, you also have to think about these things because they need to translate into concrete applications that doctor can use, not in 5 or 10 years, but in as little time as possible. And so this is another example of where exciting findings are coming, but time can be spent in a better manner. And as in the general field of AI, I think we can consider, at least for nowadays, that there are two main opportunities in using machine learning in the field of medicines. That is reducing a large complex of information, something as high-dimensional as a patient, which has a history, which has results, which has their own genome, their own habits and behaviors, and all of that needs to be taken into account for using that information in the medical field. Another opportunity is around the very complex data we're getting from some sensors. So here an EEG recording, which is incredibly difficult to read. Machine learning in this case is excellent at finding signal where there is too much information for a human brain to understand it. Knowing this, well, how do we bring the brain into that data space? And so Michael alluded to this idea, and I will spend a little bit more time on it here, which is that the brain is obviously a very complex object, and there are ways where you can look at it. You can look at it from a physiological standpoint, for instance, or even a electrical standpoint coming from the physiology or genetics. That's a kind of a lower level. Or you can look at it from a psychological or cognitive standpoint. And so this is a very important thing to consider, which is there is a level of explanation which is optimal for using machine learning today. Machine learning are computationally expensive systems, so they need CPUs, and the CPUs take time to go through numbers. So it is really important to present the right amount of numbers so that we don't spend too many years waiting for answers that if we get them, wouldn't be able to comprehend them. And so what I'm arguing here is that in order to bring the brain into the data revolution, this decade is to consider a level of explanation which is around the functional and the structural level. The reason being that this is a level of explanation that is computationally less expensive and which is sufficiently low so that there is not too much variance in what is coming out of it. But additionally, whatever results we're finding at that level is explainable from a clinical standpoint. We can see that functionally something isn't going right, and therefore we can bring it to a upper level, the cognitive level, for instance, and start to make sense of the patient's behavior. Perpendicularly to this, there is also an element of complexity. So brain scans can be a lot of data, and a lot of data can be very expensive to process. And process, even if you were successful at processing large amount of data, often the odds are that what you're finding, you're not really understanding what you're finding, because you're looking at a couple of voxels here and there, and they're not organized in a meaningful manner. On the other hand, if you look at very little information, so for instance, 4 lobe of the brain, well, you may find something that you can somewhat explain, but is it really relevant for expressing the complexity of clinical symptoms? And so what I'm arguing here is that there is a level of complexity of using the brain, of using brain scan, that we should be looking at.
I'm sorry, I think we lost your voice here. We cannot hear you.
Hello?
Yep.
Yeah.
Okay. So if we look at the two elements here, we can look at this area, which I call a sweet spot, which consider the brain as a relatively medium level of explanation, so functional and structural, along the lines of a complexity of the 379 postulation. And this is something we've used at Omniscient, and some of the results Michael presented, one of which I can present here, which is now available on the archive, actually, if you want to get access to the paper, where we mapped patients' symptoms and we mapped them against their functional areas. And we use machine learning for that, an algorithm that finds what the best prediction is and then map it to the postulation. What we found is that patients that were reporting high level of hallucination were showing anomalous activity both in the right M belt and the right PH, which are part of the auditory and the vision networks. So this is the kind of thing that machine learning enables. And bearing that in mind, we thought about bringing modern software making and start to craft softwares that would be used by clinicians. And this is the a story on how we came up with the software that Mike presented earlier called QuickTome. And QuickTome is anchored in the thinking I was presenting earlier, but is also anchored in a few of the common pitfall that we find in the field of machine learning when applied to medical science. And here, a very interesting statistic, that is 87% of science projects never make it to production. Production means that it never makes it in the hand of users, being paying customers or being generally people of the same organization that would like to use the project. In the medical field, that number is even higher. So a lot of the work gets thrown away, and we'll see why. Another interesting fact is that we had a lot of promise from AI recently. We've heard about great prowess of AI systems. But unfortunately, we're learning now that when these systems come outside of the lab, they actually struggle in various clinical situations. And part of the reason for this is that most of what people are using in labs for machine learning system is what you find on the left-hand side of this image. But really what doctors have to work with is what you find on the right-hand side. And so machine learning systems should be built on the right-hand side of the picture rather than on the left-hand side, which obviously brings all sorts of complications and requires a higher degree of technicality. The same applies for quality of scans. And here we've got a beautiful 7 Tesla scan of someone who's probably spent half a day in a scanner. But really what doctors have to work with is what you find on the right-hand side. So images that are acquired in less ideal situations. So again, software should be working with these systems. This is what we took into account when we ventured in creating QuickTome, which is software which aims at mapping abnormally shaped brain, which Mike described really well, under time pressure. So very little time to do so. And doing so on scanners that are often dated or acquired in the less ideal situations. So how did we do this? Well, first of all, we built a machine for finding solution. And that is important to mention here, is that in the field of neuroscience, we rarely find the capacities that other tech industries have in terms of cloud computing and working with data at scale. And so we built a brain lake, which is essentially a repository of patients' brain, then harmonize them and run in a distributed infrastructure, many models, some of which qualified, many of them churned and were never used. And once a model was qualified to fit for purpose, we tested it on hundreds and hundreds and hundreds of scans. And more importantly, throughout that process, at every point of the process and every day, doctors like Michael Shugru and specialists like myself were involved into reading the results, understanding the results, and making sure that they made sense from a clinical standpoint. So Michael did show this view. This is how we created this atlas that is able to consider specific shapes of the brain and patient situation. This is how, also how I created this system that Professor Theo will speak about in a moment, that detects anomalous functionality within parcellation of a specific patient's brain. Obviously, all of this wouldn't be working without the highest degree of security, which enables transmission of information massively useful for creating models, machine learning models. So once you have a good model, what needs to happen is the work of dozens and dozens of individuals taking that model and turning it into a product. It is one thing to be able to show a map that you see on a computer, but it is another to show the map in a way that actually somebody in your position can use it. And so this is again something we've done by creating an entire team of people that have worked through bringing these data science or those models to an actual product that is now QuickTone. And again, the same thing happens every step of the way. Specialists, doctors, like specialists and doctors were involved into guiding the contributors in everything they did. We've seen this UI we've put together, which helps to navigate straight to where the need of information is. We've also looked at some easy way to extract the data and bring a navigation system. So I'm reaching the conclusion of this presentation here, and I think the message I want to leave you with is to consider machine learning for what it is good for, which is at this stage mainly information reduction and complexity reduction. What we're trying to achieve here by looking at these two things is not to replace human judgment, but we're trying to bring the information that you wouldn't have not been able to get otherwise due to the sheer complexity or the volume of it, and able to essentially augment your way to look at different problems. Thank you very much for your attention.
Thank you very much, Stefan, for this excellent presentation. Most of us do not understand what's behind these algorithms you showed us. Armando, you have to.
Thank you, Stefan. Really for a normal neurosurgeon, it's not very easy to understand, but really, I take advantage. Take some photo of your slide, of course. But the last one is very important, reducing complexity to arrive to the clinical solution of the problem. But I hope that in future, that will be very, very interesting. Thank you again, Stefan.
Maybe we'll have augmented learning in our brains. We need in a few years, more or less. Okay, thank you so much.
It was also very interesting, your slide, when the relationship in between schizophrenia and hallucination. This is very, very interesting. the areas involved in those things, because it's a clinical situation that we are really in front of. This week I have a boy of 16 years old with visual hallucination, of course, and some kind of schizophrenic things. Know what was the last? Finally, it was in the hands of different doctors, psychiatrists, neurosurgeons, neurologists, etc. And nobody asked for a good MRI. So finally, we discover an AVM, very complex AVM in the calcarine area of the occipital lobe. Can you see what happened and the relationship in between the clinical situation and anatomical? And so your presentation clarify us for that. Thank you.
Well, thanks for that. The full paper is on open access if you ever like to have a look at it.
Oh, thank you. Thank you. So, Engelbert, some other.
No. Just it's only left to introduce the next speaker. And
okay, go ahead. I know him very well, but
everybody knows us at the ISMIN group. It's a pleasure to announce Charles Theo. I think in Australia, everybody knows you, and also neurosurgeons know you all wide around. It's easy to show his career. He started in Australia. He was in the US for more than 10 years, came back to Sydney, and he is the most important and outstanding neurosurgeon in Australia, I guess. Theo, just give us your talk on this difficult topic of the ISMINS. You're welcome.
Well, thank you very much, Engelbert. It's good to see old friends. Armando, it's great to see you again, and Asmi. It's a great honor to be asked to give this talk, and it's my only regret is that we couldn't do it in person and share a nice meal together and share some good times together. But anyway, let's continue with this, and this is my talk on okay, so hopefully you can see that. I will reduce this. Fantastic. Engelbert, can you see the talk?
Yeah, everything
right.
is perfect. Yeah.
Okay, so firstly, thank you to my previous speakers, Mike Chagru and Stefan Doyen, for their overview of the software program that I'll be talking about in this brief presentation. So I'm going to talk about the use of brain stimulation to reorganize the connectome for brain surgery patients for post-operative therapy. My disclaimer is I'm a consultant for Escalap. I'm a director and shareholder of Cingulum Health Clinic and co-founder of Omniscient. Well, we all see patients like this with a tumor in a very eloquent area. We take out that tumor and we often have, and thankfully more often than not, have a good outcome. Unfortunately, however, a tumor that is in almost exactly the same area with the same well-defined margins can be removed in another patient with a devastating outcome. This is not through any carelessness of the surgeon. It's not through anything to do with surgical technique. It's got everything to do with the way the brain is connected. Sometimes we can avoid it, thankfully, and other times we can't. So once we get a neurological deficit, is there anything we can do to improve the quality of life of the patient? I'd like to go through this talk with illustrations of patients, and I'm sure you all have patients similar to these with the same problems. Let me first talk about case study number 1, a 71-year-old female who presents with a very short history of headache and short-term memory loss. On examination, she's obese, unwell looking, but she's very alert and orientated. And she has some mild weakness of the upper limb, and poor short-term memory, but otherwise in pretty good neurological condition. Here's her MRI scan that shows a butterfly glioma. It shows some cortical atrophy bifrontally. And unfortunately, it also shows that the GBM is multifocal with a portion in the splenium of the corpus callosum. She was not prepared to give up. She wanted to fight this disease. She understood the consequences, and she was then consented for a keyhole right frontal craniotomy for resection of the majority of the tumor, hopefully giving her at least a 95 to 98% resection of the entire GBM. This was performed through a small mini frontal craniotomy, a transcortical approach to the glioma, and a radical macroscopic resection of the tumor, but leaving the small focus in the splenium alone, but it's still achieving probably 98% resection of the GBM. After surgery, unfortunately, she had worsening weakness of her left upper limb. She was drowsy but obeyed commands, and one was hoping that she would improve in the next few days, but unfortunately, by day 4, she was improved slightly, but still no spontaneous eye opening. She obeyed commands briskly, but she was non-verbal and looking extremely abulic. We know what the natural course of someone like this is. If they survive the acute care period, they continue to improve neurologically over the first few weeks, so that by the time 6 weeks comes along after their radiotherapy, they're often improved, but they still have evidence of abulia or hypobulia. By 6 months, they're often back to normal, but the trouble is they get recurrence on the average about 8 months after resection of the tumor, and then of course they die within 12 months. So it means that the survival period is significantly lessened in terms of quality of life because of this neurological deficit. This is what I'd like to talk about during the next 15 minutes, and how does one improve the post-operative course of someone who takes several weeks to months to regain their quality of life after pretty devastating surgery like this. Well, we all practice passive neurorehabilitation in that we often tell our patients, look, you're going to get better, give it some time. Most people get better with time. But do we really practice active interventional neurorehabilitation? What is it, and what can we do now and in the future to improve the quality of life of these patients with neurological deficits after surgery? Well, the basic principles of active interventional neurorehabilitation can be itemized as follows. Firstly, one needs to identify the goals of treatment. And in talking about case study number one, excuse me. Talking about case study number 1, the goal of treatment with her was to clearly increase her level of consciousness, reduce the poor motivation or the abulia, and hopefully improve her left upper limb strength at the same time. Once you've identified the goals of surgery, you then study the structural images to see if you can get some idea of what you should be targeting to actively intervene in her rehabilitation. In this situation, of course, we can see that we likely went through the middle frontal gyrus, superior frontal gyrus, middle frontal gyrus. and that it was well in front of the motor area. So we're looking at a middle frontal gyrus on the right side, and with our knowledge of the Human Connectome project and the Reparcelation scheme as identified by Glasser in 2017, we know that that particular area of the brain is probably something to do with one of the major networks that Mike talked about, either DMN, CEN, or salience. But unless you have the time and inclination and several hours, then it's unfortunately very onerous to figure out exactly which network may or may not have been damaged during that operation, and hence the introduction of QuickTome. In QuickTome, we look at the network montage, we look at those areas such as CEN, DMN, and salience, and with that information, we can pick appropriate targets to enhance her rehabilitation. How do we do that? Well, we come up with an anomaly program, and QuickTome has several features, and one of them will basically compare the patient's MRI scan with normals. With machine learning and this anomaly detector, we can then tell you which networks are either destroyed completely, overregulated, or underregulated, and therefore hopefully tell us how to modify those networks to achieve the optimum neurological state. This anomaly program is such where the black areas and white areas are essentially normal or too noisy to really interpret. The blue dots are where the network is underregulated or underactive. The red areas are where those networks are overregulated or overactive. And there are areas, of course, with blue, reds, whites, and blacks that are highly variable. Once we pick the targets, then we select the protocol on how to treat the patient. We're using TMS, transcranial magnetic stimulation, where when given intermittently, it can turn up an area, in other words, stimulate a network. When given as a chronic continuous theta burst stimulation, it turns down an area or down regulates it. And if you're in any doubt about what you should do, in other words, if there's blues and reds and you're not quite sure how to interpret the montage, then ITBS or stimulation usually is the modality of choice. At this stage, you should, of course, consider the goals of treatment. For example, we do know that some networks are overactive because of the destroyed network to compensate for the breakdown in the connections in that destroyed network. And of course, turning down these networks may be detrimental to the patient. So you've got to remember what you're trying to achieve and what these alternative pathways are doing when they are either shown to be overactive or underactive. We're not quite sure how TMS works. We do know that the brain is more pliable or more plastic in the time period after the TMS. So you'd need to design a program or therapy treatment in that period after TMS. For about half an hour, the brain is particularly pliable or malleable. And for example, if you're trying to improve the upper limb function, then of course you'd design a program where they would get physiotherapy of the upper limb or strengthening exercises. If the patient was drowsy, you'd be stimulating during that period, et cetera, et cetera. So let me show you some patients that we've treated with active interventional neuro rehabilitation using TMS. This is a patient of mine, a 44-year-old man with recurrent right frontal anaplastic oligo. Unfortunately, when he came back, he had T2 changes across the corpus callosum into the left forceps minor. To treat him, we performed a radical right frontal lobectomy. Here's his pre, post, and long-term follow-up MRI scan. These enhancement areas were new, indicating probable tumor recurrence. These darker areas on T1 were very bright on T2 and probably also demonstrated were indicative of recurrence. And of course, there were T1 and T2 changes in the forceps minor on the other side, which unfortunately could have meant further tumor progression to the contralateral side. He had a radical right frontal lobectomy. We continued the resection across the rostrum of the corpus callosum, but didn't go into the forceps minor because it didn't look abnormal. And thankfully we didn't, because those T2 changes resolved in the early post-operative phase, and even in the 6-week post-op scan, you could see no T1 or T2 changes on the contralateral side. Immediately post-op, he was abulic. He was not speaking at all, showed no initiation of movement or conversation, basically lay in bed, lights on, but no one at home. We know that patients can behave like that when they have a significant resection of the right frontal lobe, but we also know that their recovery takes usually weeks and sometimes months for them to return to a normal neurological status. He therefore had a Omni Scan, a functional MRI scan using the Omniscient software. And at day 5, we started transcranial magnetic stimulation. By day 7, 2 days later, he was almost back to normal, to someone who was an objective observer. And by 10 days after surgery, in other words, 5 days after treatment started, he was essentially normal with some slight flattening of his affect, and that's all. Talking, walking, smiling, laughing, and essentially back to normal. So the conclusion here was quite obvious, and that is that there was dramatic acceleration of his recovery, and we felt this was resulting from early intervention with TMS. How do we do this? Basically, this is his scan showing the deficits in the Reparcelation scheme on the right side. You can see the defaults here, but really to interpret this is very difficult. To interpret which pathways can be targeted to improve his function, difficult, and therefore we try and hone this down to a more targeted approach, if you will. And that is that we use the information from the Reparcelation and HCP project to identify the parcellations and connections of the CEN, DMN, and salience networks, thinking that this is likely the cause of his neurological deficits. Once we get that more specific information, we then place that information onto that montage or the anomaly detector montage, and that will hopefully then identify targets whereby we can improve the brain networks that have been damaged by his frontal lobectomy. This is a montage, and this is just an example of what we looked at. This is the central executive network that we're looking at here, and I think it's pretty obvious that if black is normal and white is normal, then his was extremely abnormal, with areas that were over active and other areas that were underactive. And we identified particular networks that we could stimulate or inhibit in order to improve his frontal lobe function. So this was his scan when he first presented preoperatively with significant T2 changes and changes on the contralateral side. This is him after surgery where he was abulic 24 hours after surgery. And this is him about a week later where there was complete resolution of the T2 changes, a very radical resection, and a patient that was neurologically normal. This is one that's equally as impressive, a 36-year-old man with recurrent anaplastic astrocytoma who chose not to have radiation and chemotherapy, but just surgery. After surgery, after his first surgery, he was left with some mild weakness of his left side, but he improved over the next 3 to 6 months, where by 3 months he could ride a bike and walk. By 6 months he could surf again at the beach. But unfortunately, within 18 months of the first operation, he got a recurrence and needed another operation. This is his scan showing the previous resection, and I think you can see why he had such a bad deficit with his first operation. And this is the recurrence here. The patient himself chose not to have radiation or chemotherapy. He wanted resection. We did another very radical resection, and I think it's pretty obvious what his neurological state was going to be like afterwards. This is him day 1 post-op with essentially a plegic left leg. His arm was surprisingly quite good, but a little bit weaker. We all have patients who are this bad after surgery, incredibly motivated. We know they're going to get better, but from his previous experience, it took him 3 to 6 months to improve. But after TMS, day 2 after TMS, he was at least swinging the leg forward. He needed one person to assist him. By day 3 after TMS, he could do it on his own with the assistance of a cane. Again, not very good function, but at least a reasonable strength in swinging the leg forward. And by day 4, he even had some fine movement in his ankle, which was pretty extraordinary and very rapid recovery, considering how plegic he was directly after surgery. This is now him day 5 after having a plegic leg with a radical resection of his leg area and the white matter connections of that. And then thankfully he comes back to clinic a few weeks later, showing that it took him at no time at all to get rid of the aids and walk without any assistance. So in summary, interventional neurorehabilitation requires connectomic analysis using quick-tome or functional MRI scanning. With that information, we then target specific networks that could compensate for the damaged network. We do it in rapid succession because we use CTBS as well as ITBS. And then, of course, in that time period afterwards, we personalize their rehabilitation. And then, of course, we follow them up significantly after that to ensure that there is continued gain and possibly even some more need for TMS. Why do you need a connectomic analysis? Because one size doesn't fit all, obviously. Why do you need a targeted approach? Because sometimes it's a matter of upregulating pathways on the ipsilateral side and downregulating pathways on the contralateral side. It can be as complex as that to achieve optimal rehabilitation. Personalized treatment, of course, it's the first principle of active neurorehabilitation, that it is you must define your goals. And then, of course, you've got to follow them up because sometimes they need further intervention. I just thought I'd quickly tell you what TMS is. It stands for transcranial magnetic stimulation. It's very non-invasive. It's a form of brain stimulation using electromagnetic induction. And when given as a continuous theta burst stimulation, the likely mechanism of action is the induction of neuroplasticity. So in basic terms, it brings you back to a default mode. It brings the brain back to a default mode and makes it, it accelerates plasticity, which is a natural phenomenon, but which, as we all know, the older you get takes longer. And sometimes these patients don't have that sort of time. Why do we use TMS? There are other therapeutic options such as direct transcranial, direct current stimulation. There's also invasive stimulation, but we like TMS because it's incredibly non-invasive and it has a safety profile that has been demonstrated for several decades now when it's been used in patients for depression. It is FDA approved for depression and OCD. You can use it off-label. Of course, once you tell the patient it's off-label, then you can use it for any treatment at all. Not only in post-surgical patients, but for other neurological conditions and other mental health issues. It's very non-invasive, it's very rapid, and has this safety profile that was once thought to be an incidence of 1 in 60,000 of seizures, and now that's been downplayed to it's probably 1 in every 100,000 treatments a patient may experience a seizure. And like I say, it's not destructive, it actually induces plasticity. The QuickTone product, I think you've seen, is particularly useful in patients who are undergoing surgery, not only as a preoperative planning tool, but also as a post-operative tool in order to instigate active neurorehabilitation. But the other good thing about it is it can quantitate and show the effects of TMS. I'd like to show you a patient who had a stroke. This is a young girl who had a young person's stroke. You can see the area here of stroke, and you can see that the Omni Scan has shown us the parcellations and some connections. This is before treatment, showing virtually no cortical areas around the stroke are active, and showing that there's some functional connections for compensatory areas on the other side, trying to make up for her speech deficit on this side. We gave her TMS, and from being able to speak poorly, she could speak much better after TMS. And this is several years after her stroke. So even given late in the course of someone's disease, it can still improve someone's neurological function. And look what the post-treatment scan shows. It shows that there are now more active parcellations around the cortical destructive area. And it also shows that the pathways coming from the contralateral side are much more robust now and much more easily demonstrated by this CSD DTI scan. So I'd like to conclude by saying that we all have post-operative neurological deficits. It's a natural consequence of any practice that sees and operates on brain tumours. The traditional management of these patients has always been to offer very passive rehabilitation in the form of physical therapy and basically reassuring patients that with time they're going to get better. But I don't think that's good enough. I don't think it's good enough because many of these patients are time poor. When they have GBM or malignant tumours, you know that they may succumb from their disease before they even recover from their deficits, or indeed they may experience recurrence and therefore further brain damage before they improve their quality of life. In other words, we know that people get better after stroke, but when someone is time poor with a malignant tumour, they just may not have the time to improve after the stroke or improve after the damage, and therefore live out their days with poor quality of life. Neuroplasticity is a natural phenomenon. This is not new. We know about plasticity. We know that it takes time, and unfortunately, it does take more time the older you have, and many of our patients are in that age bracket where neuroplasticity is very slow in improving function. So with our knowledge and now the easily seen and graphic representation of the multiple networks of the brain, plasticity may be enhanced and accelerated using interventions such as transcranial magnetic stimulation, thereby improving the quality of life of our patients in whom time is extremely limited. Thank you for your attention.
Thank you, Charlie.
Thank you, Charlie. Really, as usual, fantastic presentation. I have a question for you that, what is the systematic of the transcranial magnetic stimulation that's been in a patient with a glioma for how long time, et cetera, and how many sessions, and et cetera.
Look, ideally, we'd like to, in the ideal situation, all neurosurgical units should have a TMS machine in the ward, in ICU, so that you can start the process as soon as possible. But unfortunately, logistics mandates that they have to have an MRI scan. It has to be a CSD resting state MRI scan. Many of them aren't cooperative enough to do that in the immediate post-operative stage. But if they are, then that's what we do. We do a post-operative CSD Omniscient scan within 48 hours of surgery. That tells us not only our tumor resection, but it also maps the brain networks that we may have damaged and brain networks that we may stimulate to compensate for that damaged area. We then wait until they're discharged from hospital, and if they've had a keyhole approach, they're often discharged from hospital within 2 to 3 days of surgery, and we then transfer them as an outpatient to the Cingulum Health Clinic, where we then use those things that I showed you, those montages, to devise and design a treatment program. That treatment program goes for 5 working days. Each session takes about 5 to 10 minutes. And then, of course, the rehabilitation for the half hour after the treatment. And we do that 5 times a day for 5 days in a row. And of course, those interventions are totally dependent on your goals of treatment, such as physiotherapy, speech therapy, or stimulation therapy. But either way, it's done as an outpatient in a very integrated, cooperative, multidisciplinary type approach. And ideally, the sooner after surgery you do it, the better they're going to get better, the quicker they're going to get better.
And are there relapses if you stop the transcranial stimulation?
Look, the literature on TMS for depression does show that some people will do well initially and then they relapse pretty quickly. I'm talking several weeks to months after treatment, whereas most patients, it's long-term benefit. In those patients that we feel need top-ups, yeah, there's been a few that we've brought back maybe 3 months later because their improvement has been leveling off, or in fact, they're starting to deteriorate, and deteriorate not from tumor recurrence, but simply deteriorate because maybe their pathways need more stimulating. But that's unusual. In most cases, the 25 treatments in a week gives them long-term benefit and they don't relapse, of course, unless they get tumor recurrence.
Mm. Great. And you can, by knowledge, know after surgery which targets you stimulate? The question.
No. I'm not a Mike Chagru. I don't know the literature as well as Mike.
Okay.
I certainly don't know my anatomy as well as Mike. And that's the beauty of the program that Mike has developed. What he's, basically, I've told him, Mike, you've got to take all your knowledge, all the knowledge of the HCP, all the knowledge of Glass's Atlas, and you've got to make it for dummies like me. So what I'm very, very dependent on those anomaly montages to tell me exactly what to target. But no, but the whole QuickTome product will tell you what you need to target.
Okay. Then maybe a question also to Michael, whether is a lot of trial and error in the treatment with the transcranial stimulation, or is just related to the computer work?
Mike, you just on.
Sorry, it told me I was muted. One of the things to think about is this. The brain's vast and there's lots of potential targets, and we know that even if we have a good target, there may be a better one. And so let's think about this as a field, saying, okay, 4 years ago, no one had tried this in brain tumor patients because they were worried about seizures. So we were one of the first groups really doing this on a regular basis. We haven't had any seizures. We don't think it's that high of a risk. And so at first we were just trying to say, well, let's just pick if someone's weak, let's treat the motor cortex. And that doesn't always work. And there's a couple of reasons. One is if the corticospinal tract's injured, you're not gonna, if the fibers are cut, then there's no reason to stimulate that area. It's not gonna work. It's not gonna reconnect it to the spinal cord. But barring that, once you've looked at the structural data and you've looked at your architecture, you say, okay, these are the things that are an option. So the first thing is, if you look at the case that Charlie showed of the patient they rehabilitated with ebulia, the reason the guy had a good result is the salience network was still there and that we had available. So what this starts to make us think is in bad cases like that, where we're going to go in there and know that we're likely to get a deficit at the end of this, then we make sure that we at least leave good architecture somewhere that we can stimulate. So you think about the rehab before this as part of the surgical planning. But then the second thing about it is, let's say we take someone who has motor problems and we look at their tractography and the corticospinal tract's intact, but they're still weak. Well, we used to not have a good explanation of why that was, in part because we could never even do tractography on a post-operative patient immediately after surgery because the edema was too bad. Well, we actually take the edema off the scanner now. We can actually take the free water out and do tractography after that. It's an algorithm that's in our software. So we can see it almost immediately after surgery in most patients. And so if you see the tract is there, and we see it a lot of the time that maybe at the most the tract's been thinned, but it's not cut. But most of the time it's not even that. Then what you find is when you look at the functional connectivity matrix, it's that there's something that you did that caused areas inside of the network to talk to each other inappropriately. And so you might find that the best target is the SMA on the other side, something you would never have thought of. But we do know that we should be looking at the motor system and how it talks to the basal ganglia cerebellum. And we look at that connectivity. If you're treating a patient with cognitive issues or depression, the DMN salience is a good place to look. Now, the issue with it is we're using prior knowledge, and we've put all of this in there where you can just click a button and it pulls up the default node network. It's that simple. But of course, then the problem is that there may be areas that are not really cleanly part of any of those montages that are really important for this one symptom. So how do you figure that out? Well, it's simple. You collect a ton of data, you turn machine learning loose on it, then you do the thing that Stefan showed where you say, okay, if someone has sadness, particularly sadness, and it's really their only problem, what circuit in the brain is that located in? And so it might be a parcellation you hadn't thought of. That's where the data dining and machine learning comes in, is that getting down to that level of granularity and we know that that's the level of granularity that it works at, because in some cases, two parcellations that are next to each other are in totally different networks and do totally different things. But really, we know that from brain mapping. You stimulate here and there's a speech arrest, and you stimulate a centimeter away and it's not. So we kind of know that that's about the size of a functional unit in the brain. Well, digging into that, the data set that you generate when you look at 379 parcellations and all their functional connections is 144,000 data points. So you got to start coming up with places where to look. And that's a machine learning problem to get to that level of granularity. So what I would say is that in the short term, use prior knowledge, right? So we know a lot about brain networks. If someone has a cognitive problem, you start looking at the cognitive networks. If someone has an emotional problem, you look at where the mental illnesses happen. If someone has a motor problem, you look at the motor system. And what we did is we took everything that we'd ever mapped and all the network models that we've created, and we put it into one place where it's basically a point and click interface, so that you can leverage that. But we still have to be a doctor and think, what network do I think is abnormal, or what comparison? And you compare and see how these areas are talking to each other, and you pick a parcellation that's talking to a lot of areas inappropriately. And
I think, Mike, from a practical point of view, Engelbert, correct me if I'm wrong, Engelbert, but Engelbert was asking if the Omni software identifies certain networks that we can stimulate. We stimulate them, the patient doesn't get better. How do we know we've picked the right targets? I mean, are there other targets that we should have or might have stimulated to get a better result?
Well, of course, right? Now, I think that the challenge is, first, in the future, we learn from those things and we use data to start saying, how do we get better tools for picking the correct target every time? But the second thing about it is this: TMS, if it was pioneered by neurosurgeons, we would be doing it for colds, everything. But it's pioneered by psychiatrists, so that they have a very, very niche, only for depression on Tuesday and Thursday. It's the safest medical treatment we have. It's not a big deal to add a target.
Do you have a stereotactic device for both?
Yes.
For the transcranial? Yeah, okay.
Yeah, in Charlie's video, if you looked in the corner, you could see that we were targeting with it. Yeah, so you don't have to be millimetrically precise because it's the field that it delivers, but the data shows that you should be pretty much over the correct parcellation. It should be close. So we use image guidance for everybody.
It was once felt in Engelbert that TMS was pretty non-specific, and you could just for example, for depression, you could just put the magnet over the dorsolateral prefrontal cortex and get the same results as if you, every time.
Yeah.
But there are studies to show that with depression, targeting and getting a more specific networks does give you better results.
Yeah.
The trouble is they never had the software. They never had the software package to show them what to target specifically. Now that we've got it, we can be a little bit more accurate in our delivery of the TMS.
Yeah. And is there any use of bilateral transcranial stimulation, like at the DBS?
We do it all the time.
Oh, absolutely. We do that all the time. We do it both.
Okay.
Because remember, sometimes, well, I'm not quite sure how it works, but let's just presume that 15% of fibers don't cross, and therefore, you can get motor function from the ipsilateral cortex. So sometimes we see the ipsilateral cortex trying really desperately hard to compensate for the damage on the contralateral side. And if we stimulate that, then it can improve the neurological function, even though it's on the ipsilateral side. So no, bilateral stimulation is actually quite common.
Okay. So are there questions from the audience? Oh, yeah.
So someone asked about the dose of TMS. How do you calculate what percentage of motor threshold? We generally do 80% because theta burst is at 80%, and there's a lot of literature on it. It has a very low seizure risk. The only time we do anything other than 80% for theta burst, and we try to use theta burst because it's faster, it leaves a longer window, and it's equally effective, at least. But the only time we do higher is, 80% of motor threshold. And we do, only the time we do it higher is occasionally we see someone that they have no functional anomaly and the corticospinal tract is thinned out or something, or the arcuate is thinned out. And our thought is the only thing we can do positive for this patient is to make sure for sure that we maximize the synaptic plasticity of what's left. So if you have half of your tracts, we try to get more out of it. Whether we have data on that and that's useful, don't know, but it sometimes is the only thing we see. So we don't see a functional connectivity problem, and we see a tract that's been thinned out, we will use higher thresholds. But other than that, it's almost always 80%.
Mike, can you answer the question about the pediatric brain?
The answer is people are doing pediatrics in different parts of the world. There's actually someone in Australia running a phase 3 trial for TMS and autism after a phase 2 that was very successful. So there's a large grant for this. So there's a lot of people doing it. And there's a clinic in China where I think it's almost entirely pediatrics that we were at in Huashan. So there's a lot of people doing it. The challenge, of course, is obviously getting a kid to stand still for an MRI. Because if you give someone propofol or anesthesia, you're going to screw up your functional connectivity. So that makes it a little bit challenging. But again, it's definitely possible. There's definitely people doing it. There's people who can get fMRIs on babies. So with enough patients, it's possible to do it. We haven't done it a lot because most of our patients who come in are adults. We're adult doctors for the most part. So there's no reason you couldn't. I mean, it's pretty much the safest neurological treatment I know of.
Are there questions to Stefan? Armando, do you have a question?
I have a question for maybe for Charlie or for Michael also. How do you determine the parameters of stimulation? That's time, density.
Sorry, Amanda, I didn't get the gist of the question. Just say it again.
Oh, how do you determine the parameters of stimulation? That's been time, intensity, etc.
So we use a lot of the information on literature for mental health issues, depression, and OCD. So yeah, the time is about anywhere between 5 and 10 minutes, according to how many networks you're stimulating or inhibiting, and the number of treatments. It used to be that the old machines would only deliver alpha wave TMS. With the more modern machines, we can now do continuous theta burst stimulation, and again, the literature suggests that you can do that in a more rapid succession rather than spreading it out over a week or 2 or 3 weeks. We can do it all, 5 treatments in one day with the same sort of benefits. So a lot of Armando is based on literature that we've gleaned from the psychiatric experience for depression and OCD.
Oh, okay.
Believe it or not, there's actually, even though it's off-label, there's quite a bit of literature on TMS for stroke, rehabilitation, and so a lot of work has been done on TMS for off-label use.
Okay.
Any other question for the audience? No? Okay. It's 11, okay. It's 11, not 11. By after 11 here in Buenos Aires. So I don't know if, as me, as a coordinator, what your suggestion is.
I think we had a very good discussion. I think most of the question in the chat box already answered by the respective speaker. I think Jerry Lin also has shared a lot of link. If a participant interested, they can refer directly to the link. I think it's already exceed 2 hours. Usually we conducted 2 hours. It's a very interesting topic. I must thank everybody, speakers as well as the moderators for participating in this very informative and exciting session. So for your information, actually we do ISMIN webinar every 2 months. In between, we introduce a new technology. So the last one was we do a confocal microendoscopy, and this time we choose Omniscient Neurotechnology. So the next ISMIN webinar will be in 1 month's time, focusing on endovascular therapy. So please join us again in future. If you have any suggestion, especially on the new technology, just let us know. Yeah. Maybe Asra, you want to say anything?
Yes. No, maybe I would like to say something concerning to you, because I have to congratulate you enormously as a founder member of this society, one of the founder members, of course, and for your dedication, your enthusiastic work, and we hope you will continue like this, because now you are a very, very strong person with your enthusiastic way of work. Maybe Asra would like to say something also, of course.
Yeah, Asra, please, can you, because Asra's support is very important. He and his technical team from the University of Surabaya, Indonesia, is fully responsible to hold this meeting. Usually, we also have another platform, WeChat, from China. We do not know how many join us. It could be 2,000, 1,000 something. So we will let you know later. And I think Asra also having a concurrent meeting with their society right now to organize their national meeting next year. So maybe he may not be able to answer us immediately. Maybe I hope Professor Knops and Armando Basso can wrap up, and we probably close, and maybe a short message from the speaker as well.
Well, first of all, I would like to thank Stefan, Charlie Theo, Michael Chavel, for their fantastic presentation, because at least myself, I learned a lot, because this is an enormous advance for the management and understanding the problem of our patients. So congratulations to 3 of them. And maybe you, Engelbert, you'd like to say something to close the meeting?
I think everything, nothing is clear in these discussions, but I think we had wonderful presentations. I also learned for that. But one thing would be interesting, whether Stefan can augment knowledge by machines in our brain, in healthy persons, to augment knowledge. Is this a topic for you?
You're talking about the brain-machine interface, I suppose. Yeah. So there's really interesting work getting done in the space. You find that there's people that have actually decoded neural patterns and are able to extract information directly from it. So if you can do this from the brain to the machine, you can do it from the machine to the brain as well. So we'll see what the future brings. I think there's a lot of work being done there, and then we might find ourselves talking in this space in a couple of years from now, and I'll make a presentation on that.
Okay.
Yeah, we'll be waiting for that presentation in 2 years, please. Good.
That's great.
Okay.
So,
Michael,
thank you,
bye-bye.
everybody.
And, Stefan, bye-bye. Charlie, my dear Charlie,
Great work.
It was very good to see
Thank
you
you.
again.
Yeah. Probably can we have a group photo? Hope everyone can put their video on. Zara, can you take a group photo?
Let's have a group photo first.
Yeah.
1, 2, 3, smile.
And Azra?
Good.
Azra, yes, there you are.
Yeah.
Okay, send us a photo.
Yeah. Okay, thank you very much. Okay,
Thank
take care,
you.
everyone. See you. Thank you.
Bye.
Bye-bye.